let's talk about there is a soulmate for every person. So we're going to have to define some, predicates. And this is an example where we will define a predicate, i.e. a function. So let's define a predicate soulmate S, which takes as input two people, A and B. Okay, and we'll use this to return the statement, A has as soulmate, so person A has as soulmate person B. Basically, it's a very long-winded way of saying B is a soulmate for A. Okay. So we're clearly talking about people, so we could define the set of people. Okay, so the set of people, A, let's call it B. What can we use for people? Let's call people, I don't know, W is the set of people. So it's, the set of objects which I will generically refer to as W. Little w, W is a person. So I've defined a set. Okay, now, first version of that, okay, says there is one special soulmate. There is one special hardworking, I'll put special hardworking in parentheses. Okay, so there's one, just to imply that, that's not actually in the statement, but, that's what we really mean, that there's this hardworking soulmate who, such that that person is a soulmate to everyone. Okay. So what does that mean? That means that there exists a special hardworking soulmate. So there exists a special hardworking soulmate B, okay, in the set of people, okay, such that, okay, that person B, okay, so B, this person is B, is a soulmate to everyone. So what does that mean? Is a soulmate to everyone? That means that so this person B is a soulmate for all people A in the set of people. Okay, is a soulmate to everyone, i.e., so for all people A in the set of people. Okay. So for all people A in the set of people, this person is a soulmate to that person A. So for all A in the set of people, it is the case that B is a soulmate to A. But that's exactly what this predicate does. It's the case that B is a soulmate to A. So there exists this special B such that for all people A in the set of people, B is a soulmate to A. Okay, so this sentence in the first interpretation has this fairly complicated representation in math. Now, very often, we just ignore the statement of the set we're talking about because it's obvious. So we will typically say there exists B such that, for all A, it is the case that S of A, B. So I'm just removing, the set W from this picture because it's obvious that we're talking about people. Okay. Let's look at the other interpretation. So what's the other interpretation? Okay. The other interpretation is that every person has their own soulmate. So every person has their own special soulmate. Okay, so what we're saying is that for every person, for all A, it is the case that that person A has a soulmate. So it is the case that there exists a soulmate, there exists a person B, for which B is a soulmate of A. So that's represented by the predicate by saying we're going to assert the statement S of A, B. Okay, so let me read it. For all people A, so each person A, there exists a B such that B is a soulmate. Person A has as soulmate person B. B is a soulmate of A. Okay. Now, you will observe that these two interpretations of that complex sentence look very similar. The only difference is in the ordering of the quantifiers. So in going from this very hard to prove statement to this much easier to prove statement, the only thing that changed is the order of the quantifiers. Okay, so this is an example of what we call a statement that has mixed quantifiers, because it has both kinds of quantifiers. Whenever you have mixed quantifiers, okay, the order of quantifiers matters. Okay. And that's basically the end of this lecture. The next lecture is going to be about proofs. So I'm going to list some statements of a more mathematical flavor. So these are kind of English statements. I'm going to list some statements of a more mathematical flavor. And I want you to just think about what it takes, or what would it take to convince you to prove these statements to you. Don't prove them. Just think about what it would take. Okay. And now that we have quantifiers, you'll see that these statements involve quantifiers. So 1, okay, for all numbers n which are greater than 2. So this is kind of saying what's the set of things we're talking about. We're talking about numbers greater than 2. So every number greater than 2, okay, satisfies the property that, so we can assert that if n is even, okay, then n is a sum of 2 primes. So this is a conjecture due to Goldbach. Please don't try to prove this conjecture. I just want you to think about what it would take to prove the conjecture, to convince you of this conjecture. Okay, 2. There exists A, B, and C. So a triple of numbers, A, B, and C. So I'm writing that this way. Okay, there exists a triple of numbers A, B, and C, such that, so we could say that are in, okay, n, to indicate a triple, we would say n cubed. Okay, so there exists a triple of numbers A, B, C that's in the set n cubed. So it's n, this is an n, this is an n, this is an n. So it says n cubed, n, n, n. Okay, for which a squared plus b squared equals c squared. Think about what it takes to prove that to you. Okay. You might recognize that this is related to something that the great Pythagoras proved. Okay. 3. There does not exist a triple of numbers A, B, and C, okay, in n cubed, such that a cubed plus b cubed is equal to c cubed. Okay. Think about what it would take to prove this to you. This is related to something that apparently Fermat claimed to have proved. And think about, lastly, for all A, B, and C in n cubed, we are going to assert that a cubed plus b cubed is not equal to c cubed. What would it take to prove that to you? Okay. I also urge you to think about the relationship between 3 and 4. Okay, and I'll see you next lecture. But think about what it would take to prove these things to you.